So Firebolt, data analytics and cost optimization. Really what we're going to try and talk about here today is well, Firebolt and how it attacks costs. Now, there's going to be two sides to that. We're going to address more of the platform side than the operational side today, but we will touch on some of the operational side. As we know, more data, more problems, more money. So we're going to go through a bit of a demo on how Firebolt can attack this from a query optimization perspective, kind of the Firebolt way of doing things. And then, as mentioned, we're going to move into some breakout rooms and hopefully have some great discussions on both sides. So with the more data, more problems issue, we run into some trade-offs. One of the first things we'll do oftentimes as we're bringing in more and more data is we'll begin to aggregate that data in the summary tables. This gives us some problems. First off, it extends our ETL or ELT pipelines. It can become manpower intensive because if I have to build a secondary pipeline to achieve the performance of a given query, well, that's man week, generally a week to 2 weeks lost working on that summary pipeline. Another thing we can do is we can analyze smaller time windows. We can take our customers who are used to analyzing a year's worth of data and we can say, nope, we're only going to do a month or a week. The fourth or the third option is just to accept slow dashboards and frustrate the user experience. We all know that if we frustrate the user experience, then we're probably going to be affecting revenue generation rather than cutting costs. So there's a trade-off there. And then the last solution that we see quite often is pulling together multiple point solutions in very complex ways, where we use some of these very high performance data solutions as caching layers, for instance, or as secondary query engines. The problems we run into there is, of course, that creates complexity within our user base. Now they're querying two things, or worse yet, they're joining data from two separate systems. So one of the things that we've seen is slow data platforms, as I kind of touched on, makes manpower costs explode. This is not easily, it's not a normal reaction, but the reality is architects can't verify accuracy when data is too slow. For instance, if I ingest a terabyte of data and I want to make sure all the phone numbers are a phone number format, that query itself is too slow. So I can't constrain that data. If I can't constrain the data, then of course anomalies occur. BI analysts waste a whole bunch of time optimizing queries to attempt to achieve their customers' goals. That also creates communication costs between BI analysts and data engineers, which brings us to the third one. Once the BI analysts start looking for higher performance through summary optimizations, the data engineers have to implement these summary pipelines. And really what I'm seeing in the field is a lot of summary pipelines. Every one of them are expensive because it does take a week or 2 weeks to mature. All of this really comes down to one thing: platforms don't aggregate or join efficiently from a Firebolt perspective. We've built from the ground up. Our primary goal is to be efficient on these things. So a quick demo of how we pull this off. Let me get this up. There we are. I've got this window bar, sorry, kind of in the way. All right, so here we have a quick demo. This is actually from one of our customers who let us use their data. They're an ad tech shop. So we're going to see, metrics like clicks and impressions and in-app events and launches, etc. To kind of give you an idea of what's going on behind the scenes, I just want to show the tables real quick, and we can see that we have 3 tables that are important here because we can see them up here in the join. We've got LTV, which is 57 billion rows long, 31 terabytes data. We've compressed that down to 1.8 ter within Firebolt through our ability to compress and index data in our FFF file format. Then we have 2 lookup tables, one called owned apps, which is 144,000 rows, a second called account, which is 72,000 rows respectively, much smaller. but they do exist. And if we look at this query that they were running, in this case, under Looker, we can see that it's straightforward. Firebolt's not anything new, it's just SQL. So we have a CTE here, looks just like any other CTE. Selecting a bunch of stuff from LTV, we join to owned apps and then to account. And the interesting thing to note here is this app slug. I'll get back to that in a minute. Now the query isn't exactly easy. It's got a bunch of keys and group bys, and of course there's the join. And then we've got some conditions on the media source and the date time stamps of the LTV event. And remember, this is 57 billion rows long. If we run this query now, it runs in 0.37 seconds on an engine that is costing me $9 an hour. Now, to kind of show scalability, things don't scale linearly in Firebolt. We can cut that down to a much smaller engine. It's still going to run in 0.47 seconds. It's a really quick machine. Now, the speed is just one thing. The more important thing is the cost. And in this case, cost is I/O. The real advantage that Firebolt has is it moves less data because of its sparse indexing capability. It knows where every row is. Well, not every row, but knows really closely to where those rows are. So it's kind of the difference between knowing the coffee is at the grocery store and knowing which shelf the coffee is on at the grocery store. You may not know exactly where on that shelf, but Firebolt does these things behind the scenes. And when we introduce that sparse indexing, you'll notice here is we're only scanning 3.2 gig to get the answer to this massive query. Now, to do that, we do employ some technologies. One of the things we do is primary indexing. Every table in Firebolt has a primary index. This is what establishes that sparse indexing. So the most used fields that we use in where clauses, we include in that primary index. The second thing we do is secondary indexes. If we look at those, which are right here on the left, there we go. We've got two index types that we apply here. First that I want to point out is the join index. And the reason the join index exists is, remember when I mentioned that app slug field? App slug is not the primary index of owned apps. So if we're going to join on that, it's going to be uncomfortable. It's not sorted properly. So we brought in join indexes, which are really, a recreation of the old school covering indexes. Since we're joining on app slug and then selecting name, then platform, if we index on those three fields, we will materialize that index behind the scenes. So when the queries run, the materialized data is in the right order, everything will accelerate dramatically. This will give you anywhere from 2 to 10x advantage on joins. And the last piece that I want to touch on here from a development perspective is aggregating indexes. These are great fun. This allows me to do things that were not really generally possible in any SQL-based platform before. Imagine, if you will, we take analysis services and SQL Server and we turn them into one product. That's effectively what we're trying to do. An aggregating index is kind of a cross between materialized view and a functional index. So you can see this syntax is very straightforward. It looks like any other aggregate query, except we don't have the where clause and the group by clause because it's assumed. In this case, we're grouping by these attributes, and we're going to aggregate based on these attributes. And as soon as I create this aggregating index, it will maintain 100% synchronization with the base table with absolutely no user maintenance. And remember, manpower costs are part of cost too, so we want to reduce that as much as possible. This allows us to replace the whole process of summary pipelines that take a week, 2 weeks because of QA and development time, etc., and reduce that into a 5-minute rotation. I can see the query that's taking a long time. I run the show query plan on it. I can see the aggregate. I write the aggregating index, and then the end user doesn't have to do anything, because as soon as this aggregating index is in place, Firebolt's compiler will pick up on it. So the next time the user runs the same query, instead of going to the base table, it's going off to this aggregating index. And then the last thing I did want to touch on is administration tasks, because administration sometimes causes cost as well. We've seen on other platforms where t-shirt sizing exists. So as your workload increases, you really end up at a point where you have to make the decision, do I allow slower queries or do I double the size of my instance, because that's the t-shirt size. At Firebolt, we don't do that. We've got very flexible engine sizing. So here I've got 4 separate engines, one for ingestion, one for internal analytics, one for external analytics, isolating workloads, allowing me to fine tune these engines to exactly what the user or what the workload needs. This helps me, again, reduce costs because I'm not oversizing a single engine to manage 3 different workloads. And then from there, I can design these engines any way I'd like. Unlike some other platforms, I can choose any engine spec or any node type that Amazon makes available, all the way from this $1 an hour for CPU thing up to these monsters into the $22 an hour with 72 CPUs, 96 CPUs. Pick the memory and local cache that's necessary for your workload. That way, if your CPU does go up by a third, you can do something silly like just add another node rather than doubling the entire engine. So here you can see the pricing is absolutely transparent on every node type. And then once I select my node type, I can go from 1 to 128 different, 1 to 128 nodes in my cluster. And the pricing there is perfectly transparent as well. This cluster will cost me $10.40 an hour. No matter how many queries I run, no matter how many indexes on it, that's what this engine is going to cost.
Hey, Rob, we have a question coming in. Somebody is asking if we see any performance difference with window functions like lag, etc. That's from Jacob.
That really depends on how they're employed. So we have to remember all of this functionality is going to sit on top of Firebolt's indexing strategy. So if you're doing a window function on top of a field that's in an aggregated index in Firebolt compared to one that's not on another platform, then of course we're going to see a performance variation. And that does depend somewhat on how your indexes are built. If the granularity of the index on the base table is like 20 to 1, that's an easy 20 times improvement. So resuming.
I see also a hand raise. Oh. Feel free to unmute and just ask whatever you like.
One of the disadvantages, or I wouldn't say it as a disadvantage, what I've observed is whenever we have to do a primary index, it needs to be a not null. Meaning, let's say if we have data that is not yet cleansed or prepped into a certain stage, we cannot index it. Meaning there are only certain things we can index. How would you suggest we optimize our queries in this case? Because we're like addressing one more point to Jacob's question is when we have to do index or window functions, let's say to remove, do matches or using city hashes or something, it would really start dragging on. If let's say we are using a $4 engine, which is CPU optimized and also memory optimized.
Right. Generally, I would suggest in any data warehouse platform that nulls should be scrubbed. That's just a cleanliness thing in the data warehouse world. Now, once that occurs, then we don't have a problem with indexing on that field anymore. So, when I say scrubbed, we do run into cases where, let's say you've got a fact table that depends on a dimension table. You've got a slowly arriving dimension. So I loaded a fact, but the salesperson hasn't arrived yet. Really, that salesperson in the fact table should be unknown until it's known, not null. Null is different than unknown. And this is oftentimes where query processors will have trouble because null, it becomes a tri-state Boolean. If we can scrub that out to unknown until it is known, then we don't have that index problem. Does that make sense?
That is fine. Let's say with the industry we work on, it is difficult to scrub the data, and I'm trying to find where it's an optimal situation. Let's say we have less number of indexing possibilities, but yet we need to use all the data points that is available out there to operate with a window function. Would you suggest then going with a more a higher t-shirt size engine, or you would suggest get your data order in first and then think of optimizations in the higher t-shirt size?
It's again, this is one of those things where it's hard to say which is right. Obviously, with my background as a data architect, my reaction is always going to be the same. Cost reductions will start with proper data models. From there, we can start working on platform issues. So if the data model is secure and subject-oriented, time-variant, all that fun stuff, then, and this is assuming a data warehouse workload, then we can only get so far with the model itself. That's reality. Physics does exist. At that point, to deal with it, then we can get into things like engine sizing. Now, engine sizing can go a number of different directions, depending on your workload. If you've got a high concurrency workload, we might want to think about scaling out. If we've got a low concurrency, complex workload, we might want to be thinking of scaling up. But that does take us out of the t-shirt sizing world because we have so much available to custom size these engines. Does that answer your question?
Let me enhance it a little bit more with another point. Is we let's say there is I'm aware that there isn't Kafka streams yet available where you can just ingest tons and tons of data, but we can do micro batching, correct? In a micro batching where you're directly consuming from lots of other feeds, which can give you certain data which cannot be cleansed in the first levels itself or in the first staging tables itself.
Sure.
But still you need to run a lot of cleansing where you employ a lot of window functions. This is where we would, again, what we're in our use case where with Firebolt, what we are trying to do is we are employing a much higher engine or a t-shirt size. Would there be, if the indexing possibilities increases, then it would be much easier. So for example, if I have to do a many-to-many calculation, then it would help me much faster.
Understood. And, really, I'm not sure I can quite answer your question on your workload. I haven't seen this workload.
Okay.
I can answer generalities, and generally we can do that. Now, the other thing is we can do much of this cleansing in flight. Since external tables, as you know, are just tables, we can build complex queries on them and do the lookups on in flight on ingest. That is a possibility, which removes that secondary transformation completely, and in theory should reduce costs. Now, that's not an always thing because no two workloads are alike. But if I can lift something out of S3, enrich it by joining it to two other tables while it's in flight, ingesting from that external table, and then commit it to an internal table, that's one step, which should be much lighter on the pocketbook than two steps of, staging it up and then doing the transform. Does that make sense?
That completely makes sense. Thanks again.
No problem. Where are we at? So Rick G asked, did I say null doesn't mean not known? Yes, this is one of my things. You'll hear from me from time to time, and this has nothing to do with Firebolt. This is an old architecture argument. Null can mean not known, of course, or null can be not known. Of course, it can also mean unavailable. The third possibility is it might mean that this thing just doesn't have one of those things by design. And the problem that we run into there is we don't know that it's null which one of those three things it is. So we can't tell for sure how to deal with that. And that's just problematic in the SQL world. Since we do allow nulls, tri-state booleans are going to be problematic on virtually every platform. Sorry about that. So I'd like to continue on here. So really what we're shooting for with Firebolt is an unbelievably fast and efficient platform. We want to deliver sub-second analytic queries at terabyte scale, as we saw in the demo. Obviously, we want to be a modern cloud-native architecture with the coupled storage and compute, fairly easy to manage infrastructure. And we want to build a system that's simple for developers and data engineers. Everything in Firebolt is just SQL. There's no new languages. There's no secondary development platform, etc. So it's a modern architecture, we believe, for tomorrow's data challenges. Again, cloud native from the ground up, decoupled storage and compute. Engines are highly tunable. We can implement one project and engine at a time along the current stack. We can live nicely in the ecosystem with other data platforms. I did go through aggregating indexes and joint indexes in the demo. And of course, Firebolt deals with high concurrency. We really do handle extreme cases of parallel queries. We're not like other platforms where you'll see, mail slots, etc., concurrency issues stopping your workloads. And then, of course, cloud storage is cheap, but it does tend to rack up a bit as you increase your data size. The reason this is important is, again, the secondary pipelines add volume to the data set. Aggregating indexes are tiny by comparison. If we can leverage them, we can again reduce that cost. So back to optimizing cost directly, we're trying to push a new level of hardware efficiency. It's not just fast, it's primarily about efficiency. Now, fast is good. We can dial the numbers up and down. So if I do need more speed, I can spend more money. If I just want less cost, I can keep the speed at the current speed and we can get to where we need to go. The other thing that's really important about Firebolt is there's no contracts, no upfront commitments. It's all pay as you go. You jump into the system, you fire up an engine for $1 an hour, it's going to cost $1 an hour. If you run it for 30 minutes, it's going to cost 50 cents.